Welcome to the deep dive. Today, we're headed back to school. Well, sort of.
Back to school.
Yeah. But don't worry, this isn't the geometry that puts you to sleep. We're going deep into Geometry Revisited.
Ah, a classic.
And get this, it's not about proofs and equations. It's about the beauty and power of, well, geometric thinking.
I like where this is going.
You actually requested this deep dive,
I did. Wanted to brush up on the basics.
but also peek beyond, right? Beyond the basic shapes and all.
Exactly.
So get ready for some elegant results, unexpected connections, maybe even reignite that love of learning from way back when.
You're hitting all the right notes. Geometry is so much more than we learned back in high school. I mean, it's always evolving.
Evolving. How can geometry evolve? It's just shapes, isn't it?
Right. It might seem that way, but there's this line in Geometry Revisited that really struck me. It says, geometry still possesses all those virtues that the educators ascribed to it a generation ago. Moreover, it is even more useful and necessary to the scientist and practical mathematician than it has ever been.
More useful now than ever. I'm intrigued. Tell me more.
Well, think about it. We're using geometry to map orbits of satellites, understand the structure of molecules, even to grasp space-time.
Wow. I never thought of it that way.
It's a language, an essential language for describing the universe.
Okay, I'm starting to see it. Geometry. Way more than just triangles on a whiteboard. So let's get to the fun stuff.
Let's.
Triangles, we all know them, maybe even love them.
Ah, yes, triangles. They might seem basic, but they're full of surprises.
More than just the Pythagorean theorem. I'm listening.
Oh, absolutely. Take the extended law of sines, for example. It goes beyond the basic ratio of sides and angles.
Extended law of sines. Okay, I vaguely remember the law of sines from school, but what's extended about it?
It connects those ratios, the sides and angles, to the circumradius of the triangle.
Circumradius. Remind me what that is again.
Sure, the circumradius is the radius of the circle that passes through all 3 points of the triangle, the circumcircle. So basically, this law links the triangle's sides and angles to this bigger idea, the circle that goes around it.
It's like we're connecting something familiar, the triangle, with this bigger idea.
Exactly. And that connection gives the extended law of sines its power. You can use it to figure out things about the triangle based on the circle and vice versa.
Now let's talk about something I remember struggling with. Siva's theorem. What is that all about?
Siva's theorem, well, it's a neat idea. It tells us when 3 lines inside a triangle will all intersect at one point.
Okay, I need a visual. Give me an example.
Think about the medians of a triangle.
The lines from each corner to the midpoint of the opposite side.
Precisely. Siva's theorem tells us those medians will always meet at a special point, the centroid.
Right, the centroid. It's like the balancing point.
It is. And here's something that blew my mind. The centroid divides each median in a specific ratio, 2:1. So the part from the corner to the centroid is twice as long as the part from the centroid to the midpoint.
Wow, I never knew that. It's amazing how even a simple triangle has these hidden relationships. Speaking of hidden things, what about the 9-point circle? It always sounded kind of magical to me.
It is pretty amazing. Every triangle has this special circle associated with it, and it goes through 9 specific points.
Okay, walk me through those 9 points.
All right, you've got the midpoint of each side of the triangle, then the foot of each altitude.
That's where the altitude hits the side, right?
Yes, the point where the altitude intersects the side, so that's 6 points. The last 3 are the midpoints of the segments connecting each corner to the orthocenter.
Orthocenter, just to remind everyone, is where the 3 altitudes meet.
Exactly. So you've got these 9 points, and incredibly, they all lie on a single circle. It's like a hidden blueprint within every triangle.
That's pretty wild. But wait, there's more. There's a connection between this 9-point circle and the circumcircle we talked about earlier.
You're right. The 9-point circle has a radius that's exactly half the radius of the circumcircle.
No way. That's incredible. Are there any other connections I should know about?
Definitely. The center of the 9-point circle, it sits exactly halfway between the circumcenter and the orthocenter.
These connections are so elegant. I'm starting to see why you find geometry so fascinating.
It's all about these unexpected relationships, these hidden patterns. And you know what? We've only just begun to explore.
Okay, I'm still trying to wrap my head around that 9-point circle. But I'm ready for more. What about those petal triangles?
Petal triangles, huh? They're another great example of how, simple constructions can lead to some surprising results.
Yeah.
You start with any triangle, right?
Okay.
Then you pick a point. Could be inside the triangle, outside, doesn't matter.
That's the petal point, right?
Exactly. And then from that point, you draw perpendiculars to each side of the triangle.
Perpendicular lines, got it.
And where those lines meet the sides of the triangle, Those are the corners of your new triangle, the petal triangle.
Ah, so each petal point makes a different petal triangle. Interesting.
Yeah, and the position of that petal point can really change the look of that petal triangle. All sorts of shapes and relationships pop up depending on where you put it.
Okay, so give me an example. What kind of surprising things can happen?
This one's pretty wild. If you keep making petal triangles, right, of petal triangles, using the same petal point each time, eventually they start to look like the original triangle. They become similar.
Ooh, it's like a geometric echo. The shape reappears in these smaller triangles. Okay, petal triangles, officially cool. What about this power of a point thing? It sounds kind of mysterious.
It does have a ring to it, doesn't it? But really, it's all about a point's relationship to a circle.
So how does that work?
Imagine a circle, any circle, and a point. That point could be inside, outside, even on the circle itself. The power of a point helps us understand the distances. Like, if you draw lines from that point to the circle, the power tells you something about the lengths of those lines.
Can you give me a real example? How's it useful?
Sure. Let's say you want to find the length of a tangent. A line from a point outside the circle, just touching the circle. The power of a point can help you calculate that length.
So it's not just some abstract concept. It has real uses.
Exactly. It's a pretty versatile tool.
All right, I'm curious about Simpson lines now. Even the name sounds interesting.
Simpson lines are a classic example of finding something beautiful and unexpected in geometry. So picture this. You pick any point on the circumcircle of a triangle.
Okay, circumcircle, I remember. Goes through all three corners.
Right. Now, from that point on the circumcircle, you draw perpendicular lines to each side of the triangle.
Perpendiculars, got it. Then what?
Well, the points where those lines hit the sides of the triangle, those 3 points, they'll always be on a straight line.
No way. So no matter what point I pick on the circle, those 3 points line up.
Every single time. And that line, that's the Simpson line, named after Robert Simpson, a Scottish mathematician.
Okay, you've got my attention. Now, this Simpson line, does it connect to anything else in geometry?
It does. You can actually use it to prove Ptolemy's theorem.
Ptolemy's theorem, huh?
Yeah, it's a theorem about cyclic quadrilaterals.
Oh, remind me, a cyclic quadrilateral is a four-sided shape where all 4 corners are on a circle, right?
Exactly. And Ptolemy's theorem tells us something about the lengths of the sides and the diagonals of that quadrilateral.
Okay, and what does it say?
It says that if you multiply the lengths of the diagonals, it'll be equal to the sum of the products of the opposite sides. Bit of mouthful, but elegant.
Wow, it's amazing how something simple, like those perpendicular lines, can connect to a whole theorem. Like everything in geometry is linked somehow.
I know, it's beautiful, isn't it? The Simpson line, it creates this bridge between a simple idea and a complex theorem.
This is making me think about geometry differently. It's not just shapes sitting there. It's about how they move and relate to each other. Which brings us to transformations.
Transformations are all about shifting our perspective, seeing what stays the same, even when things are moving around.
All right, ready for a perspective shift. What kind of transformations are we talking about here?
Well, Geometry Revisited focuses on 3 main types. We've got translations, rotations, and reflections.
Okay, break those down for me.
Sure, translations, that's like sliding a shape. You don't change its orientation, just its position, like moving a piece of furniture across the room.
Right, makes sense.
Rotations are like spinning the shape, like a wheel turning.
And reflections are like flipping the shape. Mirror image. I think I'm starting to remember these, but why are they so important in geometry?
What's fascinating is you can combine these transformations, right, to make really complex movements. But even through all that, some properties stay the same.
So we're seeing what's fundamental about a shape. What makes it that shape even when it moves?
Exactly. It's about understanding the essence of the object.
Can you give me an example? What kind of properties stay the same?
Let's take a triangle again. You can translate it all over the place, slide it around, but its area never changes.
Oh, that's interesting.
And you can actually use that fact that a triangle's area is unchanged by translation to prove other things, like a new tool in your geometry toolbox.
Okay, transformations. I'm seeing the light. Now let's switch gears to something that sounds more like a puzzle. The 3-jug problem.
Oh, the 3-jug problem, a classic. It's a great way to see how geometry can solve a problem that doesn't even seem geometric at first.
All right, lay it on me. What's the puzzle?
Okay, so imagine you've got 3 jugs, different sizes, right? And you have as much liquid as you need. The challenge is to measure out a specific amount of liquid, but you can only use those jugs.
Okay, so I can fill them, empty them, pour between them. I see where this could get tricky.
Right. And the way we bring geometry in is through something called trilinear coordinates.
Trilinear coordinates. I'm picturing a triangle, but how does that help us with jugs?
Picture an equilateral triangle. Each point inside that triangle, it represents a different way the liquid could be distributed in the jugs.
So, like, the corners of the triangle are the jugs.
Not quite. The corners are when one jug is completely full, the other two are empty. The position of the point inside the triangle tells you how much liquid is in each jug.
So as I pour liquid between the jugs, that point moves around inside the triangle.
Exactly. And the rules of the puzzle, like only being able to fill or empty jugs, they become rules about how that point can move. It's a whole geometric system for understanding the problem.
So we took a puzzle about jugs and turned it into a puzzle about a point in a triangle.
It's pretty neat, right? We can represent problems in different ways. Leads to all sorts of insights.
I'm seeing the geometry is way more versatile than I thought. We've gone from shapes to moving things around to puzzles. It's like a language, a way to understand the world.
I like that. A language. And speaking of languages, there's one more concept we need to talk about. Duality.
Duality. Okay, now you've got my attention.
Yeah.
That sounds deep. Duality, huh? So what is duality in geometry?
Well, it's the idea that points and lines can switch roles. Like, what was a point can become a line. And a line, it turns into a point.
Wait, hold on. How's that even possible? I'm trying to picture it, and my brain's doing backflips.
It is a mind-bending concept.
Right.
It comes from an area of geometry called projective geometry.
Projective geometry.
Yeah, it focuses on properties that stay the same even when we project shapes onto different surfaces.
Like how a shadow changes shape depending on where the light's coming from.
Exactly. Projective geometry wants to understand what's constant, even with those changes in perspective. And duality is a big part of that. Here's an example.
Okay, give me something I can visualize.
All right, so imagine a circle and a point outside that circle. Now, picture drawing lines from that point that just graze the circle, tangents.
Tangents, got it.
With duality, that point outside the circle, it could transform into a line. And you know what happens to those tangents?
They become points.
Exactly. Those tangents, which were lines, they become points on this new line that represents our original point. It's a swap. Points and lines trading places.
Wow, that's pretty amazing. So this isn't just some theoretical idea. It has real visual meaning.
Oh, absolutely. Duality leads to some really powerful theorems in projective geometry, helps us understand shapes in a new way, and it actually connects back to those conics we talked about, ellipses, parabolas, hyperbolas.
Okay, how do conics fit into all of this?
Well, remember we said conics are formed by slicing a cone with a plane? Turns out each conic can also be seen as a transformation of a circle. It's a process called reciprocation.
So you're saying I can take a circle, apply this duality magic, and poof, I get an ellipse. Or a parabola.
That's the idea. Another example of how everything in geometry is connected, sometimes in really surprising ways.
My mind is officially blown. We've covered so much ground today. The law of sines, Sieve's theorem, 9-point circle, pedal triangles, power of a point, Simpson lines, transformations, even the three-jug problem. And now duality and conics.
It's been quite a journey.
I feel like I've rediscovered geometry. Like there's this whole world of math I thought I knew, but it's so much deeper.
It's been a pleasure exploring it with you. Geometry is full of beauty, and it really is a language for understanding the universe.
You know, what really sticks with me is duality. Points and lines, switching roles, it's wild. Makes me wonder what other hidden connections are out there in geometry, just waiting to be discovered.
That's a great question. And honestly, it's something mathematicians are still working on. We only touched on projective geometry and transformations today. Imagine what's out there when you start thinking about more than 3 dimensions.
More than 3 dimensions. Whoa, that's getting a little too mind-bending for me right now.
It is a challenge to visualize, for sure, but that's part of the fun of math, right? Exploring things beyond what we can see and touch every day. Who knows what incredible shapes are out there in higher dimensions just waiting to be found.
I love that thought. And hey, if any of our listeners are feeling as inspired as I am, I highly recommend checking out the full Geometry Revisited. It's packed with cool proofs and ideas.
I agree. And remember, geometry is all around us. Keep your eyes open, stay curious, and you might just discover something amazing yourself.
That's a great note to end on. Thanks for joining us on this geometric adventure, everyone. We'll be back next time with another deep dive into a new world of ideas.